So what we have is we have a pot. So I've got my protractor down here on the table, and it goes from 300, of course, 0 to 365 degrees. And I've got my pointer pointing at 0. So what we're going to do is we're going to measure the actual maximum degrees that this pot can turn. I'm over, start turning, and here is where it hits its end stop right there. Can y'all see about what it is? It's not 350 degrees, because 310, looks like 308. It's off a little bit, so we'll use 308 for this guy to calculate our voltages. 310, let's use 310. It's just going to cause it to be off really just a little bit when we do our math. Are we okay? So 310 degrees is the maximum rotation of this pot. So we got to know the maximum rotation of the pot before we can calculate our transfer function. So this is the circuit that I have hooked up. I've got 12 volts coming in at the top of the pot. And then I got my wiper connected to my multimeter. And then, of course, I got common. So we measured our maximum degrees of rotation. So I'll need to make a note of this, right? So step one, we measured what? 310 degrees. So I've got the circuit constructed already. It was a real simple circuit to construct because I just hooked up a 12-volt power supply across the pot, then hooked up my meter up. So the circuit looks like this. Okay. So this is the common for my my power supply and the common for my meter. This is the red lead on my meter, and then the yellow. This is coming from the variable supply that I have set for 12 volts. So here's my circuit. Okay. You can see we have 12 volts applied to it, 11.99, but that'll be close enough to 12 volts so we can use it as our math anyway, because I'm the one that's going to be turning the pot, so it's going to depend on my accuracy too. So we got 12 volts applied to it, and it would be almost impossible for me to get exactly 12 volts on a pot anyway. I mean, on the power supply anyway. So we have the circuit wired up, and what we're trying to do now is calculate the transfer function. So out, we're getting voltage out, we're putting degrees in, so my maximum voltage out would be 12 volts, and then of course my maximum degree would be equal to 310, which is what we're using. So here's my circuit, and then we're going to do the transfer function. Let me get my pen out. So it's out, so we're getting voltage out. The maximum voltage we can get out is 12. My transfer function would be equal to the maximum out, which would be 12, and we're putting in 310 degrees. So my answer is going to be in volts per degree. So what would our transfer function be? 308 millivolts. Everybody okay? And Brown's okay. I'm asking. 38. Oh, I'm sorry. 38 point what? 0.7. Yeah, millivolts. So we need to carry it out that far to be accurate at all. Millivolts per degree. So now what we can do, now that we know our transfer function, y'all have that written down, right? Then we can come in and fill up this table. So what we're going to do is we're going to use this part right here. This is figure 1. This is the first circuit. And then my maximum degree is going to be 310 down here. And then we're going to compute our voltage, and then we're going to measure our voltage to see how we do that. So if transfer function is equal to out over in, right? And then, of course, what we're trying to do is calculate out. So transfer function is equal to out over in. Okay. And then what I'm going to do is I'm going to take my n in degrees. So all these over here. So so I'm sorry, so out would be equal to what? My transfer function times my number of degrees. So what we're going to do now is y'all going to go down through here and do this chart. We're going to do this guy right here, and we're going to calculate our anticipated voltage we're going to get out for each one of these degrees. So I'm going to go ahead and pause this and give y'all time to, I'll do the first one just to make sure. So I'm going to bring up my calculator. I'm going to take 30, and then I'm going to multiply it by my transfer function, which was 38.7 milli, right, to the minus third. So we should expect about 1.2 volts, right? Everybody okay with that now? So we should be able to come back and do the rest of them. And there will be transfer functions on the test, so anybody that's having a problem with this need to let me know now. Once we come up and get the answers, we'll make sure everybody's got the right one. 1.16 or 1.2, 1.16, 1.2 is what we're going to put down. We might as well, the pot is I'm not that accurate, right? You understand? Because I'm going to be looking at the protractor and turning this. So 1.2 is, 1.2 is what I'm going to put down. Well, it's Ohm's law. So what we did is we had our transfer function is out over N, and then we said, okay, my transfer function would be equal. We're getting volts out. It's a maximum voltage out, maximum degrees. So we're getting an output. Our output of the pot is a voltage, and the input, which is I'm turning, is degrees. So what I do is I use the maximum voltage that we can get out over the maximum degrees, which was 310 degrees. When we did the math, we came up with 38.7 millivolts. Okay. Now, once we got that, we can take this formula just like we did in Ohm's law. This is the beauty about a three-term formula, is you can put it inside this thing that transposes the formula for it. So I'm trying to calculate my voltage, which is out. So I'm trying to calculate out. So out would be equal to my transfer function times my N, which is degrees. So what I did, and this is basically what you did in Ohm's law, right? So what I say is I come up in, I didn't want to do that, guys. So sorry. I need to learn how to do that. I mean, I know how to do it, but I would come over here and I would say my transfer function would be equal to my degrees, which would be 30. I mean, sorry, my out would be equal to 30 degrees times my transfer function, which is 38.7 millivolts times 10 to the minus third. And it come up and gave me 1.2 volts. You see that, Jalen? Yeah, once you get a three-term formula, and transfer functions are always out over N. So I'm turning the pot, so that's my N, right? And my out, when I measure it on this lead right here, this is my out. My N is me turning my pot. So out would be, the maximum I can get would be what? 12 volts at my maximum degrees, which would be 310, which is what we measured. So we should expect approximately 1.2 volts for that one right there. And they should go up every time, right? You understand that? So if you come up with a smaller answer than your previous one, it means you had to do something wrong. So what do we get for 45 degrees? Anybody got that? Anybody got 90? Yeah, that's good enough. 8.1 and 210. 10.8. And of course this is going to be maximum, so this will be about 12 volts. Everybody agree with that? Anybody want to see them worked? Okay guys, what we're going to do, I'm going to switch back over to my camera. And then y'all keep up with the degrees for me, right? Y'all got the degrees for me? Y'all got them down, because I'm not going to be able to see this when I switch over to my camera. Okay. So if you can't see the meter, it's got a glare on it. I could come up here every time and put a piece of paper over there so y'all can see it. But I'm going to come up here and turn this to 30 degrees, as close as I can get it. So we calculated 1.2. We're measuring 889 millivolts. Are we okay? So what's that? About 400 millivolts off. And then what's our next one after 30? I'm listening. 45. I get 45 as close as I can, guys. That's 45, 1.5, 1.6 volts. Yeah, we're going to just round it up. 1.6 volts. Are we okay? And what's the next one? Okay. So that's as close as 90 as I can get. About 3.4 volts. Okay, then what's our next one? Well, I can get in front of it, can I? 210. We'll move it around to 210. Okay, that's about the best I can do. 8.2 volts. And what's next? There's 280. As close as I can get it. 11.5 volts. And the last one would be 210, which should be 12.01 volts. So you see, yeah. Yeah. Okay. So what was the problem? Why didn't it come up to be exactly what we calculated? On all of them. So the first one, you notice I did a little better on the top, but most of the time that's human error. But it's close enough where we can come up and we can actually see how we could calculate what this thing would be out. So if I wanted to, of course, we use a potentiometer to measure position of something, right? So instead of me turning this, this could be attached physically to something, and then we could tell by the voltage that we get off this thing exactly what degrees that my thing was at. Yeah, that looks pretty good. So any questions on that? Okay, guys, y'all take a 15-minute break. Sorry, let me go find another 1K resistor, and then we'll come back. And then I'll bring up my PowerPoint. So this is the new circuit that we're hooking up. So what we're going to do is we're going to deliberately set the span of this thing. So we're no longer going to have from 0 to 12. We're going to set our span between what voltage we calculate be to there relative to common. So this is our common. And then what voltage we're going to have here relative to common. And then we'll recalculate the span. So y'all calculate those voltages for me. It's just nothing but a series circuit. So when we calculate that, and it's a 10K pot, we just calculate it as a 3-element series circuit. That's all we do. So this would be a 3.3K, and then this right here would be a, yeah. Oh, sorry. Hold on. You can't see this, Brianna? Hold on a second. What's that? See what? Okay, what you might need to do is log off and log back on. So I'm going to pause the lecture and let me know when you get back. I forgot to say you could have probably hit F5 and that might have worked too, but that's okay. Everything's working. Okay. So what we're going to do is calculate our span. So we're going to calculate it like a series circuit, because technically this right here, we're going to run this unloaded. My meter has about 15 megohms worth of resistance on it. So that means my meter is not going to affect the voltage divider at all. So we can consider, when we calculate our voltages, we can consider this to be an open because it's 15 meg relative to 11K if I put it all the way up. We still have 12 volts up here, hopefully. We'll check that. And then this is a 10K. That's their pot. It's a 10K pot. And then we have a 1K ohm right there. And what we're trying to do is we're trying to calculate if I was to take a voltmeter and measure at the top of the pot all the way to common. And then we'll calculate this. And if we call this V1 and then V2, then the span of the pot would be the maximum on the pot would be equal to, we'll look at that. All right, guys, I'm going to pause this. Y'all calculate that for me. So anybody got V1 yet? Anybody got it? Somebody said, was that you, Christian? Or Crow? 8.8. Okay. Yeah, but that's how much it's dropping. What we're trying to do is calculate what's left over. So what we're doing is we're using Kirchhoff's law, so it'll be 8.8 volts across these two right here. That looks about right. Okay. And then V2, anybody got that? Which used to be the voltage across the 1K. Come on, guys, this is DC. Y'all probably thought y'd never use these formulas again, but guess what? Y'all were wrong. And if you take solid state, which is a part of the ILT program, in fact, I think it's up in the core, we'll be using these formulas again. So it's really, really neat what we do, and it brings back why do you learn all these formulas in DC? Because they apply to solid state circuits, amplifier circuits, and all that other kind of stuff. Same formulas. So when if you take solid state, there's very few formulas you're going to have to know because most of them we're just going to come up and adopt from DC. So what would V2 equal to? So V2 would be equal, I'm listening. Anybody got it? Well, what you're trying to do, we're going to use Kirchhoff's law. So let's say we calculate it using current. I would probably use what we call the voltage divider formula, but let's say we calculate current. So I'd say IT, what, would be equal to V divided by what would be RT. Okay, so 14.3K, right? And then what would IT be equal to? Now, I'll show y'all a formula called the voltage divider formula that is a lot faster because you got to do one calculation, but we'll do it this way first. So what I'm going to do is I'm going to calculate, we need to give these resistors numbers for it to make sense. We'll call this R1, we'll call this R2, and we'll call this R3. So I'll calculate VR1 would be equal to 3.3K times 839 microamps, and that would give me the voltage drop across this resistor right there. Okay, 2.7 volts, but that's not what V1's going to measure. V1's going to measure what's left. So according to Kirchhoff's law, the voltage, so this is going to drop 2.7 volts, but what did we start off with? We started off with 12. So V1, which is going to be right there, V1 is going to measure 12 minus 2.7. Because that's what's left over, right? Does that make sense? So we're using Kirchhoff's voltage law to say, okay, I calculate voltage drop, and that's the problem. People will calculate this, and that's what they want to use, but I'm not measuring across VR1. I don't know. I'm doing this. We'll look and see. We'll look and see who's correct. I mean, we're doing it one way. I didn't say this was correct. We'll come back and figure it out. Yeah, we're using Kirchhoff's law. So what did y'all come up with? Can't be 9.3. It's a 1K. You can't say the one. Yeah, you can't say. Here you can use, VR2 is the voltage, so VR1 is the voltage drop across R2 and R3, but VR2 is just the voltage drop across R3, because all we're doing is measuring across R3. So what did we give us this, what did we get right here? You can't, 12 minus 2.7. We're up here. Let's get this one first. 9.3, is that right? So we got two answers. Well, what I'm going to do is I'm going to come back and just kind of check. I'm going to say the voltage drop. I can add these two in my head. So what most people want to do is they want to start up here, right? You understand? But we could have started where? Here. So I could say, okay, V1 would be equal to 11K times 839 microamps. Y'all see that? So basically, I don't have to use Kirchhoff's law anymore, because I said, okay, I know my current, so all I got to do is just do what? Treat this as one resistor. So what did we come up with there? Hopefully, did y'all come up with 9.3? Looks like it's pretty close to, okay. Now, the problem here is that it's not a problem, and it's fine. This is probably the way that you learned it in DC. But the ratio of a voltage that a resistor drops would be relative to all the resistors in the circuit. So what we do is we have what we call a voltage divider formula, where I could come up here and I can say VR1 would be equal to the ratio. So this would be 3.3K divided by, what was RT? 14.3. K is going to cancel out. It's on the top and bottom. And then I can multiply this by 12 and see if you don't come up and get, what took? So we call this the voltage divider formula. So what would happen is that once I know this ratio, then I can change the voltage. The ratio that a resistor drops in a series circuit will always remain the same if you don't change the circuit. So the problem y'all have, if I change this to 15 volts, then you would have to recalculate everything. But if I knew this ratio, it would always be the same. So I could say, VR2 would be equal to 1K over 14.3K times 12. And what do y'all come up with there? This is 2 over. Should come up and get 9.3. Is that right? 1K, I'm sorry. I forgot to put the K up there. K cancels out. So what you do when you use the voltage divider formula is you don't have to calculate current. So what it does is it leaves off one formula that you can make a mistake with. And so this is the way you can calculate voltage in a series circuit. So the formula is VRX. So this is the resistor you want to find the voltage drop across, times the value of Rx over RT. And then you multiply that times the source voltage, and that will give you the voltage drop across any resistor in a series circuit without calculating what? Without calculating current. So what do we get for VR2? I'm sorry, this was VR1. So what do we get for VR2? So VR2 would be equal, according to this formula, VR2 would be equal to 1K divided by 14.3K. Since the K is on the top and bottom, they cancel it out. Multiplied by 12, what did we get for VR2? I heard that, but I wasn't ready for the answer yet, so I appreciate it. So this is actually 9.3, right? So what would be the span of our pot? Well, what should we get out maximum on our pot? The maximum should be 9.3, and the minimum should be 839 millivolts, or around 1 volt. When I get down to, the minimum would be around 1 volt. Okay. So now we got to figure out how we calculate these degrees back on this guy right here. So figure 2, we got to compute our voltage at each one. Of course, I know this one down here is going to be 9.3 volts. And I know this one right here. So what would it be at 30 degrees? So let's figure out. Somebody tell me what we need to do, because dang, I keep doing that. Dang it. So what would be our range? I know my range is going to be between 9.3 and 839 millivolts. So I know when I get it all the way up here, I'll have 9.3, and I know when I get it down to here, I'll have 839 millivolts. And I know up here I'll have 9.3. So what would I have at 30 degrees? So my transfer function is going to equal to what? Yeah, but here we got, so the maximum I would get out would be 9.3 millivolts, right? So we know that's the max. And we'll see if this works out. Well, it'll be maximum out, and this is going to equal to 310 degrees, right? Well, we don't get 12 anymore because 12 is the maximum I can get out. It's not what's applied to the circuit. It's the maximum the pot would give you out. This pot now will never, ever, 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 ever give me out 12 volts. So if I come over here and bring up my camera again, okay. So when I turn my pot all the way to 310 degrees, I get 9.24 volts. We calculated 9.3, but that's pretty good, guys. So what we're saying is that it's the maximum you get out, right? It's not what's applied to your circuit. It's what the maximum we'll get out. So does that make sense? So that's pretty good, guys. We calculated 9.3 and we're getting 9.24, but it might not be exactly 12 volts anymore. So we'll make it work. So there we go. And then the minimum we calculated 800 and something millivolts. So we got 830 millivolts. I'm not going to change my thing. We calculated 839, right? That makes sense. So that's really good math, guys. Y'all did a really good job here. Off the what? Yes. Yeah, 8.4. 8.4 is the range, right? Does that make sense? Yeah. So that would be what we call our span. So a while ago, our span was from 0 to 12, but here our span is going to be 9.3 to 830 something millivolts, and we can measure it more accurately. Let's put it here. 837. What did we calculate? 839. Good gracious. Is that what we calculated? 839. Good gracious, guys. That's really close. That's 2 millivolts off. That's really good. And then of course up here, this is really good too. 8.3, 9.3. So this is really good too. So let's figure out how we're going to do our voltages in this chart. I know this down here is going to be 9.3, but what would it be at 30 millivolts? I'm sorry, 30 degrees. So I'll let y'all do this and see if we can come up. So what did we get on our measured over here? I forgot to write that down, guys. For 30 degrees, we got what? We don't say 0.89. Yeah. Okay, that's okay. 45 degrees. 90 degrees. 12. And what have we computed this over here yet? Nope, we don't use 0.9, right? That's okay. 900 millivolts, 0.45 degrees. $90 degrees. 210. Okay, we'll bring up the camera. We'll measure this. Dang, I keep doing that. Dang it. So give them to me again. 900 millivolts. Then what was 45 degrees? And 9. Okay, so this is 0 degrees. We've got 830 millivolts. This is 30 degrees. We have 1.3 volts. What's the next one? There's 45. 45's hard. What's the next? Okay, that's 45. What's the next one? 3.1. Next. 210, 6.5. 280, 8.9. And 9.3. Oops. Dang it. So what do we measure? At 30? At 30 degrees? Okay, at 45? At 90? At 210? At 280? So not bad, guys. It looks like the pod is not quite linear down at the very bottom when we came over and did this, but the closer we get, it looks like the better it gets. Then, of course, here we have 9.3. All right, guys, what we're going to do is we'll start the test at 11:30, which gives y'all time to go back and review for the test. And then, everybody okay? Any questions? So that's the lab, guys. Well, what we did is we calculated our transfer function, and it would be a little different, but the maximum we can get out is 9.3 volts, and 9.3 volts would be at 310 degrees. So this gives us our transfer function. What would that give us, Jalen? You got that? I don't know. What is that? 30 millivolts. Everybody agree with that? For our transfer function, was that right? Okay. So when we get our so once we get our transfer function, then we say, okay, my output, just like we did a while ago, my output would be equal to the transfer function times the degrees. So this is going to be 30 milli times 30 degrees, which gives us around, oh, I can do that in my head. This would be 900 millivolts. So we're doing the same thing we was doing a while ago. It's just that here we set the span on the pot. So instead of us going from 12 volts to 0, we're going from 9.3 down to 800 and I'm sorry, to 810. 11:30. Test starts at 11:30. So that should give y'all plenty of time to go back and do the previous test. There's only 31 questions on that, and then we'll start the test at 11:30. Everybody's gonna have to log into to Collaborate, which y'all know y'all can. You'll have to leave your microphone on, and everybody got a camera. I would like for y'all to turn y'all's camera on, so I can see your pretty faces, because y'all can see mine. Okay? All right, guys. I don't care. I don't care. I don't care. In fact, we might get a good laugh at you, Dalen. So you might want to go and do something funny with your hair. That would be neat. So, so everybody okay? All right. 11:30. Is that going to be okay? We can start it a little earlier. We can't start it later, but we can start it a little earlier if y'all want to. But 11:30. 11:30 okay with everybody? All right. All right. 11:30. I'm going to set my alarm. If y'all are, is everybody still there? Sorry, is everybody still there? What I'll do, I'll provide y'all the password to Collaborate message, okay? All right. And I'll tell the people that when they come back too. All right. What you need to do is just snap a picture of your tables and stuff and just turn it in before next class. Just like we would do, and I'll send out a text on that too. Thank you. That's James Roy. Yeah, I forgot to record these over here, but I'll leave it up. Let me pause my lecture.